All right, this last section in this unit really isn't too much new, but it is a little bit tricky to kind of think through exactly what we need. So I'm going to just work through an example here to show you how all this stuff works. But essentially, we're going to be taking some absolute maximums and minimums stuff, and we're going to be putting it in our cost, revenue, profit examples. So let's just first talk a little bit about optimization in general. Whoops. What optimization actually is. So we're going to be finding absolute max and absolute mins of a function. For us, for the most part, we're going to be looking at profit and revenue functions. There's a couple of examples where we'll look at maybe finding minimum costs. There's a nice inventory control problem that we can look at where you can try and minimize the cost of storing and producing items to sell. So we're going to be looking at either absolute maximums or minimums depending on the context. Obviously, for profit and revenue, we're going to care about maximizing those, trying to find the absolute max. There's lots of other examples that we can look at, some geometry type things and stuff like that. There are those in peppered throughout the practice problems, but I'm going to mostly care about these cost, revenue, profit examples. The main thing is that we need to know what function we're optimizing, and sometimes we'll have to build that function using other information. Now, in our context, it's not going to be too much of a big deal because for revenue functions, we know that revenue is quantity times price. That's our lowercase p. And profit is revenue minus cost. So building those functions is something that we're pretty used to. So that shouldn't be too bad. With geometry examples, it's all going to be based on the context. If you've got some sort of an area function, then maybe you've got some sort of a formula that represents a side length of whatever you're finding the area of, and you'll use that to multiply side lengths to get area. I don't know. For us, it's not going to be too different from what we've normally done. We are going to need a domain for the function. I'll walk us through how that works in our example. In every example, we're going to be just asking questions about what's the biggest value that we can have for this x variable or whatever our input variable is, and what's the smallest value. We're going to hope that this is a closed interval. Hope. Ooh, that's really bad. Let me fix that. We're going to hope. There we go. It's closed. The main reason we're going to hope that we get a closed interval for the domain is because then we can use the extreme value theorem, or at the very least, we've got the option to do it. If we don't get to use the extreme value theorem, if we have an open interval, remember from the last video that we can get lucky and just have a single critical number on that domain. Then we'd have to check and see if it's a local maximum or a local minimum. And if it's a local maximum, it's the absolute maximum. And if it's a local minimum, it's the absolute minimum on that domain. So for that, we'll either use the first derivative test or the second derivative test that we found. We're going to find that in a lot of these examples, the second derivative test is actually really easy to use. But I'll try and show off the extreme value theorem, first derivative test, and second derivative test for these. So you can make up your mind about what you'd like to do here. But sometimes you'll be kind of stuck in context. Maybe you won't have a closed interval, and so you can't use the extreme value theorem stuff. Maybe you won't be able to deal with the second derivative very easily, and so that's kind of out. I don't know. There's lots of different ways that we can think about this. So what we want to do is go through an example and just kind of show you how this works, what we're really looking for. So here's our example. We've got this office supply company that sells large packs of pens where the monthly cost is C of X equals 5,000 plus 2X, and the price demand equation is P equals 10 minus 0.01X, and X is the number of packs sold per month, and P is the price that we're charging for there. Before we do any sort of optimization stuff, we're going to find the domain, we're going to find the revenue, and we're going to find the profit here. We're basically just going to set everything up so we don't have to keep coming back to our setup and finding those things. So for the domain, maybe I'll type this so it's a little bit more clear. For the domain, there's really going to be two questions that we ask. First is, what's the smallest amount of things we can sell? And the second is, what's the most we can sell? Now, this first question is very easy. Since X is our production, or the number of things that we're selling, we know that the smallest amount is 0. For the biggest amount, that's a little bit tricky, and we have to think about our price-demand equation. The biggest amount is going to come when our price is smallest, so really, this is going to happen at the smallest price, or when P equals 0. So let's go ahead and put 0 into our price-demand equation for P, and now we can solve for X. And we're going to divide by 0.01, and that's going to be 1,000, I believe. 10 divided by 0.01, yeah, that should be 1,000. So what we've just done for our domain is gotten an inequality here. The lowest amount is 0. X has to be bigger than or equal to that. And the biggest amount is 1,000. That's when our price is 0. Literally, we can't give away more than 1,000 of these things a month. If we were just going to be giving them away for free, the most that we could do is 1,000. So this is our domain. So I'll put that in green. For revenue, then, we know that revenue is always the same. It's quantity times price. So we'll take X times our price-demand equation. There's a decimal in there. So we've got 10x minus 0.01 x squared. And we know that profit is always the same kind of thing. Profit is revenue minus cost. So that means P of X is 10x minus 0.01 x squared minus our cost function here. So I'm going to say negative 0.01 x squared. Then we have 10x minus 2x. So that's 8x minus 5,000. So there's our profit. So domain, revenue, profit. The domain is going to be the weirdest part. We've got to ask these two questions always. What's the smallest amount of items? What's the most amount of items? The largest amount. And it happens that the largest amount happens when we have the smallest price. Most of the time, you won't have to build that domain. We'll just be given a domain along with our setup. But every now and then, they won't give one to you, or maybe I won't give one to you. So this is how you'd find it. Cool. All right, so if this is all the information that we've got, maybe I'll kind of add this to the next slide. What we want to do is find the maximum revenue here. So we'll go back and say our revenue function is this. Let me write that out really quick. I'm going to put this up here. Revenue was 10x minus 0.01 x squared. And the domain was 1,000 was the biggest? Yeah. From 0 up to x up to 1,000. So we want to find three things. We're going to find the maximum revenue. We're going to find the quantity needed. That's the x value that we need. And then we're going to find the price that we need to charge. Most of the time, you'll actually only be asked for one of these things, maybe two, but I just want to go through all three of them so that you can see how to interpret your different answers. So find some of this stuff. We'll realistically find the x value first, maybe, I don't know, and then we can kind of go ahead and interpret our answer using the right context. So what we really want to do is, if I type this out really quickly, what this question is really asking us to do is find the absolute max of R of X. And I guess we could really say on this, maybe I'll say this, on 0 is less than X up to 1,000. Closed interval, continuous function. So if we want, we can use the extreme value theorem, but I'll show you how to do it without. Either way, no matter how you start, we're going to have to find critical numbers, which probably isn't a surprise. Pretty much everything in this unit, we've been starting off with the derivative, finding the partition numbers, and then checking to see if they're critical. So the derivative is going to be not too hard. Neat. Critical numbers. We know that as long as they're in this domain, they're good. So we'll look for partition numbers that are in this domain. So if I set this equal to 0, I've got 0.02x equals 10. So x is going to be, that's one too many zeros, 500 if you divide both sides. Since that's in the domain, that's critical. So we've got a critical number of x equals 500. Now, a decent amount of people typically stop there. And I'll warn you, if you look up optimization problems on YouTube and you find other people that will walk you through optimization problems, a lot of them are lazy and they stop here, and that's not right. What you have to show me is that this is actually the quantity that you will need to maximize the revenue. The way to find that is to show me that this actually gives an absolute maximum on this function. There are 3 ways of doing this. So our critical number was 500. I'm just going to write up our information here. R of x was 10 minus 0.01x, and r prime of x was, this is 10x minus 0.01x squared, 10 minus 0.02x. So this is the information from the other slide that I just don't want to have to go back and forth all the time. So we have 3 methods of showing that this is the absolute maximum. We can use the extreme value theorem, which says, let's just give ourselves a little table of values. We want endpoints and critical points. So if these are our x values, we want to check the revenue here. The 3 values we want to look at are 0, 500, and 1,000. We can plug these into our revenue function and see what we get. Both of the endpoints will actually be pretty easy in this case. I know right off the bat that if I plug 0 into this function, r of 0 is equal to 0. If you plug 1,000 into this function, you should also get 0. I'll let you check that. Oops, I put r of 0 instead. There we go. And so what you need to do is check and see what you'd get here. I'm going to leave this blank for now. I'll fill it in later, but I'll let you kind of pause and figure out what's going on there. Hopefully, this will give you a maximum. That's one of the options you can do. Another way of doing this is by using the first derivative test. This is the sign chart. So we can say we're looking at x values from 0 up to 500. And from 500 up to 1,000, and we're going to look at what the derivative is. So let's plug in a number like 1 here, something in between 0 and 500. If we plug in 1 here, you can get 10 minus 0.02. That is going to be positive. And if you plug in a number like 700, for instance, you're going to get 10 minus 14. If you plug 700 into this thing, 0.02 times 700 is 14. 10 minus 14 is negative. That means your function increases, decreases. Holy heck. That's a max right here. Since it's the only critical point, it's the absolute max, which is good. So the first derivative test says it was an absolute maximum. Let's check the second derivative test. The second derivative test is actually really easy here, because the second derivative of revenue is just negative 0.02. So if you plug in 500 into that second derivative, you will get a negative number. It's negative 0.02, meaning your function is concave down. You've got a horizontal tangent line. That means this point is a max. So go back, check your calculation for this, make sure that you actually do get a maximum revenue here, and we'll see all 3 match up. All right, you should get 2,500 here, which means this is the max revenue as well, because 2,500 is bigger than 0 and it's bigger than 0. Those are our only other options. So all 3 of these things say that the maximum revenue occurs at 500 units being sold. Now, this is the quantity. So for the quantity, maybe I'll clear out some space here. For the quantity, actually, you know what? I'm just going to erase some stuff. Let me get rid of the first and second derivative test. That line's not wanting to erase. Here we go. All right, and I'll get rid of this. So for the quantity, we have, using the first derivative test, second derivative test, and the extreme value theorem, that x is 500. X is your quantity. There we go. the actual revenue that we needed, or the maximum revenue, is R of 500, which you just found was $2,500. So the maximum revenue is $2,500 here, and it happens when we sell 500 units. The price is when we plug this quantity into our price demand equation. P is equal to 10 minus 0.01 times X 500. This is 10 minus 5, $5. So the quantity that we want to sell is 500 of these. The revenue that we will earn if we do that is $2,500, and we will do that by selling these at $5 a piece. That is our optimal situation here. That's the most revenue that we can earn, and that's our optimal price to earn it. That's the amount of things that we have to sell to earn that. You have to make sure that you show me using either the extreme value theorem, first derivative test, or second derivative test, that actually is the optimal solution, the maximum. Let's do the exact same thing, but we're going to do it with the profit function now. And we're going to see that it's actually a little bit different here. So let me go back a bit and find my profit function. Here it is. 0.0, well, I think I can remember this. Profit, I'll write this here. Negative 0.01 x squared plus 8x minus 500, 5,000. There. So I think I had this going in red, so let me do that in red. Oops. Profit is that. I should have just written it here right off the bat. Oh well. What we're going to do is the exact same process. We're going to find the critical points. Then we're going to check those and make sure that we actually find the maximum of this on this interval. Same interval that we used earlier. So notice the domain that we pick is the domain for all of our functions that we're using. All right, so pause this, give yourself 10 minutes, I don't know how long it'll take, and see if you can get yourself through this problem, and then I'll start filling in the blanks once you're back. All right, so this is what we've got. Derivative is negative 0.02x plus 8. A little bit different now. When we set this equal to 0, we're going to have negative 0.02x plus 8. So that means 0.02x equals 8. So x is going to be 400 when you divide 0.02 on both sides. Since that's in this interval, that is critical. Hooray. We can do the extreme value theorem. I'll just do that right now. We're going to look at x values here. Oops, I'm still on the straight line. Get rid of that. There we go. X values here. But now we're going to be looking at what happens when you plug them into the profit function. So we're going to look at 0. We're going to look at 400. And we're going to look at 1,000. So when we plug these in, give me a second, I'll have to figure out what these are. That's going to be negative 5,000. This one is negative 3,400. And this one is negative 7,000. Oof. Okay, so why is this a bad thing? Well, because our profit, no matter what, is negative. This is our maximum profit. Not very good. Our maximum profit that we can earn in this business is negative $3,400. Our model is terrible here. Oh, well. Let's check the first derivative test and second derivative test and see if that matches what we had. So, first derivative test means sign chart. We're going to go from 0 up to 400. From 400 up to 1,000. And we're going to look at the derivative of our profit function, which is this, negative 0.02x plus 8. Negative 0.02x plus 8. Good enough for me. I'll plug in something like 1. And you'll notice that if you plug in 1, you get 8 minus 0.02. That's going to be positive. And if you plug in something like 700 again, you're going to get negative 14 plus 8. That's negative. So that means your profit function is increasing, decreasing. There is a maximum right here at x equals 400. So there's your first derivative test. Second derivative test is, again, actually really easy. The second derivative is, again, just negative 0.02. So no matter what you plug into this, you're going to get negative 0.02, which is negative, meaning you've got a horizontal tangent line with something that's concave down. So there's a maximum there. So again, in any of your three options, we can say, great, the maximum profit occurs at this quantity. Oops, let me get rid of that. At the quantity x equals 400. The actual profit there, oops, let me write it like this, that we will get if we try and maximize our profit, that's supposed to be a P of 400, we said was negative $3,400. Terrible. This is a bad setup. And the price that we need to charge to get that is going to be P equals 10 minus 0.01 times 400. So notice this is 10 minus 4, or $6. So notice that this maximum profit occurs at a different place than the maximum revenue, which is okay. That should make a little bit of sense. I'll draw a picture of this and show you why in a little bit. But I do want to point out that just because we're actually able to make a positive profit, our costs are so big here that we'll never really get to outweigh those. And the reason is that our overhead cost is so big. That $5,000, if I go back, is really, really big, and it kind of outweighs everything. So if we kind of played with our model a little bit and we were able to shrink that overhead cost, things might work out a little bit. I used to play with one where you got everything the way that you thought it would. You got this nice big profit and blah, blah, blah. But I like showing this off because even though it's a negative profit, it is our best option. Or really, I guess our best option would be to close up shop and not run this business. Anyways, let me show you why revenue and profit occur at different places, or the maximum revenue and profit occur at different places. So I'm going to just draw a nice little graph, and I'm going to draw all three of our functions on here. So actually, I'm going to move this over here. So I'm not going to put any sort of a scale on here, but let's say that green is our revenue function. It typically will look something like this in a lot of our cases. And we'll make red our cost function here, where we've got these 2 points. These intersection points are our break-even points. You've probably seen that in our textbook or in other instances or anything like that. The break-even points are where cost and revenue are the same, or where profit is equal to 0. Now, what we're going to notice is that profit is actually the difference in between these things. So we've got this negative profit over here where cost is too big, and all of this stuff is our positive profit. Now, our maximum revenue is probably right around here. But if profit is the distance between these things, then I'll just draw a little line here to represent that there's not a very big distance, but here there's a much bigger distance in between revenue and cost. Revenue is higher than cost here. Now, in our example, our cost function was actually way up here. Because of that big overhead cost, it was shifted way up. But this is typically what happens. So our absolute maximum in the profit function, which normally looks something like this. Oh, I didn't draw this very well. Let me see if I can fix that. There is right around here. All right, not perfect. The break-even points should match up with these x-intercepts where profit is 0, but my drawing is a little off. Oh, well. But there's our profit. That's our maximum. It's that biggest distance here. So even though our revenue is tallest over here, it's still very, very close to the cost. So there's not a lot of separation. So These are the only types of optimization problems you'll have to really worry about. It's the ones with revenue and cost. So get familiar with those. There's several examples that you can go through in the homework or in the practice problems or whatever on here. Take a look at some of the other types of examples with some geometry and things like that, because they're very interesting, although they're not necessary in this course. But if you've figured this stuff out, really, you're going to be good. Make sure that you can go back and interpret everything. Make sure that you can use the first derivative, second derivative, or extreme value theorem. You only have to use one of those, but make sure you can use one to justify what you're saying.